This week we will focus on the waveform and the process of seeing sounds and sound properties on screen. This week's content will focus on defining timbre, the overtone series, and explore ways in which we can see sounds and their properties. We will be understanding the fundamental terminology associated with the musical terms tone color, resonance, and noise. And we'll be exploring how we can see and edit sounds and their properties on a computer and a digital audio workstation. We will begin by focusing on the objective terminology associated with the tone color and noise. We can then see how these concepts are shown on screen in a digital audio workstation and how we can use this information to edit audio. First, we must discuss timbre. Timbre is the quality and character of a sound beyond just frequency and amplitude. We also refer to a sound's timbre as tone color. It is the personality of a sound. Every sound has a unique timbre, including our voices. We must discuss how these things occur and how are the makeup of an instrument or a person's anatomy gives them a certain timbre or voice. Timbre is determined by the physical makeup of a sound source and how vibrations resonate within it. Resonance occurs when a vibrating body causes another object or surface to vibrate sympathetically, thus creating a louder and more vibrant tone. We see a picture here of the inside of a violin. This is where the resonance of the violin occurs. If we think about how a violin makes sound, there is a whole process that happens that creates the particular timbre we associate with a violin. If the violin was made out of different materials, if the violin was a different size or shape, if the violin had a different resonant body, or if the strings were made out of something different or a different size, all of those things would contribute to a different color or a different timbre. We can see a graphical two-dimensional model of a sound's characteristics through the waveform. The waveform shows a sound's frequency and amplitude, but it also shows timbre and even its amplitude envelope. Last week we talked about frequency and amplitude of a wave. Waveforms are more complex. They show us through the bumps and valleys, peaks and valleys in a wave, how overtones color the sound and resonance. Waves can be periodic or aperiodic. If a waveform has a repeated pattern, it is periodic. Periodic waveforms have a definite pitch since our brains can detect this pattern. If a waveform does not have a discernible pattern, it is aperiodic. Aperiodic waveforms are considered to be noise, since our brains cannot detect a pattern and therefore cannot detect a pitch. In this example here, our trumpet waveform has a frequency that is the same as our trombone waveform. Those two sounds are similar, but we can see by the bumps involved in the trombone versus the trumpet frequency that there are higher bumps in this one than there are in this one. The resonance of the instrument determines this pattern of overtones and therefore contributes to its timbre. A sound's unique periodic waveform helps us to visualize its timbre, as well as its frequency and amplitude. Here we see the waveforms of 4 instruments who are all playing the same note and at the same amplitude. Notice their unique shapes. So we have a violin who has a pattern that is this unique, repeating in the same fashion and at the same height as our trumpet, flute, and oboe. Notice the unique shapes of each instrument's timbre. They each have the same length of waveform or the speed of the waveform or the height of the waveform, but they all have unique bumps in their patterns. Therefore, they have a different timbre. This is very similar to fingerprints or other attributes that make something unique. The amount of bumps in the waveform are related to the amount of overtones and resonance that are resonating in the sound. Overtones in an overtone series are determined by the physical makeup and the resonance of an instrument. The overtone series itself is a natural phenomenon that provides for us a master list of possible overtones that one can use to color a note. Think of the overtone series as a spectrum of possible options to color a sound. A note's fundamental is the pitch that we hear. The overtones above it come from the overtone series and are determined by the physical makeup of an instrument or sound source. Overtones are selected from this overtone series and are usually found to have differing amplitudes. We typically do not hear individual overtones, but rather they combine to help color a sound. Our brains hear and perceive overtones in combinations, much in the same way that we see colors. Colors are usually a combination of primary colors or secondary colors, and those combinations contribute to different shades or hues that we are familiar with. Speaking of shades and hues, we can also view the overtones of a sound through a different view than the waveform. A spectrogram is a visual representation of a sound's frequency spectrum over time. It shows us a sound's fundamental and its overtone structure, even as it changes. That is to say, a sound's overtone structure changes depending on the type of performance or changing of a note. Perhaps it's being darkened or brightened by the time it begins and ends. So a spectrogram will allow us to see a sound's timbral properties as they change over time. As we look at the two examples of spectrograms here, we can see that one is noisier than the other. One of them has a scattering of overtones in a randomized sort of way. The bottom one, however, is much more organized. If we can see these tiers of overtones as the sound comes to life from left to right. This is the overtone series in action. We can see the overtones stacking on top of each other in a very ordered way and in an organized fashion. Therefore, we can see also that this is a noise and this is a pitch. We can rely upon 4 basic wave shapes to help us understand how overtones color a fundamental pitch. They are algorithmically or mathematically generated and named after the shapes their overtones create. The sine wave is our most basic waveform as it has only a fundamental note and no overtones. It is a theoretical wave, of course, because everything in the natural world has overtones in it. A sine wave, however, is a sound without any overtones. The square wave has a fundamental, but it also is colored with the odd overtones from the entire overtone series. So the first, the third, the fifth, and etc., on into infinity. The overtones are louder, so it sounds brighter than the next one. A triangle wave has a similar structure as a square wave, with only the odd overtones from the series. However, the overtones are quieter, so it sounds a bit darker than square wave. And finally, our sawtooth wave has a fundamental with all overtones from the overtone series present. It sounds the brightest and the buzziest. So these are named after their shapes. All of the overtones in these waves contribute to its resemblance of a square or a triangle and a sawtooth shape, but they also tend to show kind of how they sound. The bottom example here is noise. If I go back to this, you can see that the noise waveform is random. There is not an ordered pattern, and therefore it does not give us a sense of pitch. The human brain cannot perceive a pitch or a tone through noise. However, we can mathematically generate noise that has different characteristics to imply a change. Like the 4 basic waveforms, we can also generate noise mathematically. White noise is what we tend to think about when we think of noise. White noise is a randomized set of frequencies with equal amplitude across the entire spectrum. It is what we hear when we tune our TV, our analog TVs, to a channel that doesn't exist, or maybe a radio station in between. It's essentially what we think about when we think about white noise. We can generate other quote-unquote colors of noise, much in the same way that we can generate other shades of light or color. Pink noise is randomized frequencies, as white noise is, but with less amplitude over the course of an octave, so it reduces the overtones by -3 decibels per octave. It sounds like light rain or wind. Finally, brown noise is a set of randomized frequencies with even less amplitude, so it sounds like heavy rain or crashing waves, losing 6 decibels per octave. You can see the spectrum that they generate in these spectrograms on the screen. White noise is very flat, pink noise is darker, and brown noise is even darker than that. We can similarly continue to color sound by passing them through filters. Filters can edit the timbre of a sound. An audio filter takes out some of the overtones while leaving others. Filters are useful. They sculpt and enhance timbral properties of sounds or recordings. Think of the treble and bass controls of a car stereo. They do the same things. High-pass filters filter out low frequencies and pass the high frequencies above a cutoff frequency value. Low-pass filters filter out the high frequencies and pass the low frequencies below a cutoff frequency value. You can see these at work over here. So a high-pass filter has a cutoff frequency and will pass the frequencies above it. Our low-pass filter will pass the low frequencies. And band-pass filter also has a similar, it's like a low-pass and high-pass filter combined. It determines a range or a band of frequencies to pass and will reject the rest. Of course, if we have a band-pass filter, we can also have a band reject filter, which looks opposite of this example here, where it will pass all the other frequencies, but will block a certain band of them. In summary, we can generate timbre or color, and we can also control the timbre or color of a sound. All of these properties show us the ability for us to control these elements in sound and also see them on screen.